Today, the goal of my presentation here is to present a fundamental problem with covariance propagation, notably as it is practiced in ensemble-based schemes, but also how this extends to other data assimilation implementations as well. And now this presentation is going to be a little bit different in that I am going to talk a lot about this problem with covariance propagation, but not give any general solutions. There are some ideas for solutions out there, which I will talk about at the end, but really the goal here is to try to establish this issue with covariance propagation so that we can then move forward to try to work on solutions. So covariance propagation is encountered across data assimilation implementations, and the general framework for covariance propagation is defined as follows. So we have a dynamical model M that we use to describe the evolution of our state estimate K, where we may have some additive model error term in the form of this eta here. And then we end up using this same model, or possibly a linearization of it, to define covariance propagation in these different data assimilation frameworks. And so the first framework we can start with is simply the Kalman filter. And so in the Kalman filter, we of course construct a linearization of our state dynamics represented by this matrix M. We then define the corresponding state propagation equation here, and then following from the definition of the covariance, we get the very familiar covariance propagation equation inside the Kalman filter, where we may have this plus Q model error covariance term if we assume, of course, that eta is uncorrelated with our state. Now, in Kalman filters, it's very easy to see how covariance propagation works, but covariances are evolved in the other schemes as well. In ensemble-based methods, this may be a little less obvious, but the general framework in these types of situations occurs where we generate an initial ensemble of states, and then we evolve that ensemble according to the full dynamical model here. And then at some given time, we can then estimate the covariance matrix using the sample covariance estimator here, whether we actually construct this covariance matrix explicitly or through its square root factorizations. Now, the evolution of the covariance in these ensemble-based schemes occurs through the evolution of these ensemble members, these Qi k plus 1s. And this becomes a bit more obvious if we simply substitute this dynamics equation in here, and we can start to see that the evolution of the covariance, as I said, occurs through the evolution of these individual ensemble members in these schemes. Now, covariance propagation also occurs in variational-based schemes as well, in particular in 4D bar, but this is done implicitly, particularly through the optimization step. And this idea was noted actually going back to Jaświński in the 1970s, and then started to kind of reappear during the beginnings of 4D var in the early 1990s. Now, if we focus on ensemble-based methods, it's well established that we can construct these discrete dynamical models for accurate propagation of the state. And so one typically assumes if that the evolution of our ensemble members is reasonably accurate, then the corresponding ensemble-based covariance propagation is also reasonable, up to sampling error. Now, there's a vast body of literature out there dedicated to addressing issues with sampling error. But what I'm going to talk about today is that the covariances that we get in these contexts are actually surprisingly inaccurate, much more than what you would expect from sampling error, and it becomes particularly problematic as these correlation lengths become really small and approach grid scale. Now, intuitively, this makes sense. For a fixed grid scale as correlation lengths shrink, we start to maybe have resolution issues, particularly in regions perpendicular to the covariance diagonal where we can't resolve the dynamics. But what I'm going to show today is that the problem here is actually more basic than that. And in fact, the underlying problem that we see in these covariances is actually an inconsistency between discrete covariance propagation, which is built from the state dynamics that I showed on the previous slide, and the solutions to the continuum covariance dynamics that we actually have access to and can study in the problems that I will discuss today. Now, this work is motivated by the chemical constituent data assimilation community, and today I'm going to illustrate the inaccuracy of these covariances in the context of two examples. The first set of examples is going to come from work by Richard Menard and co-authors focusing on this stratospheric ozone transport. So in this example, we're going to consider states Q that represent the concentration of stratospheric ozone as it's being vected along an isentropic surface in the Earth's atmosphere. Now, it turns out that the continuum variance sigma squared also satisfies the advection equation for this problem. And if we consider an initial variance that is a constant value of 1, it turns out that the variance for all space and time remains a constant value of 1, to which we can compare to. Now, this first example here comes from Menard et al. In 2000, where we are looking at a plot of the variance extracted from this full-rank propagation, this MMP transpose, plotted along this isentropic surface. And the scale here corresponds to where white are values of a variance of 1, and anything in grayscale are variances that are less than 1. Now recall, in this problem, the exact variance should remain a constant value of 1 for all time, but what we can see is that the variances from this MMP transpose do not preserve that property. In particular, the variances are severely inaccurate, especially in the southern hemispheric region here, where if you look very closely, you can see that we've lost almost half of the variance in this region. Now, fast forward about 20 years, and Richard and a different set of co-authors took this same dynamical setup, but instead looked at the variances from ensemble-based propagation. And so in this example here, we're looking at the total normalized variance on the y-axis as a function of time for two different ensemble sizes denoted by the x in the circles, and then three different initial correlation length scales that correspond to larger correlations for these top curves that then decrease as we go down. And so what we see again in this example, the total variance should remain a constant value of 1, but all of these experiments result in significantly inaccurate variances, particularly as these correlation length scales become small, where this lower curve here corresponds to the smallest correlation length, and by the end of this forecasting window, we can see almost 80% of the total variance has been lost. Now, in both of these works, what was observed is that there seems to be a connection between this variance loss and shrinking correlation length scales in these regions. And we can see this illustrated quite nicely in this figure here on the right from Richard's 2021 paper, where we're looking at correlations with respect to this location here in the southern hemisphere. And so what we can see is that in this surf zone where there's very strong wind shear, as correlations are elongated along the flow, perpendicular to the flow, correlation lengths start to shrink. And as these correlation lengths start to shrink, we can see a striking resemblance to the regions of variance loss in this MMP transpose, and as the authors note in this 2021 paper, is associated with this variance loss in these ensemble-based schemes. And so I'll just say that from the outset, this was a very simple problem. We're just trying to evolve the variance that should remain constant in time. But both of these methods seem to be struggling significantly, and there is some connection to these shrinking correlation length scales in the dynamics. Now, the next example that I'm going to show is from some more recent work where we can actually take a step back and look at the one-dimensional problem. And the advantage here is that in the 1D problem, we can write down all of the equations, the continuum equations, look at the solutions, and compare them to what's being done in discrete space to really paint a complete picture to understand why these variances and the covariances are as inaccurate as they are. So in this example, we're going to consider states Q that live on the unit circle that satisfy this, what I refer to as this energy conservation equation here. Now, this equation can arise if Q, say, is the square root of some mass conserving quantity, and one can define a corresponding energy in this case and then show that the energy in the system is conserved. Now, for these numerical experiments, I'm going to take a very standard approach. I'm going to begin by discretizing this state using a numerical method that preserves this energy conservation property, and then move forward to then define the covariance propagation. So in particular, I'm going to generate initial ensembles where I'm going to draw them from a Gaussian where I've constructed the covariance matrices using the standard Gaspari cone correlation function that is a function of this cutoff length parameter C. And then given that initial ensemble, I'm going to propagate them forward in time using this discrete state propagation equation. And then at some fixed time, I'm just going to simply estimate the mean, the variance, and the covariance from the sample statistics. Now, before I move on, I want to note here that it turns out we also have a explicit PDE for both the continuum variance sigma squared and the continuum covariance, which is given here. And so what's nice is that not only do I have these equations, but for the velocity field I've chosen, I actually have exact solutions to the variance, the covariance, and the state equation I showed on the previous slide. And so in these examples, I'll be able to compute explicit errors, where I will compare the exact solutions to these equations to approximations from the sample mean and the covariance from these evolved ensembles. Now in this example here, I'm going to show animations of the evolution of all these quantities, but before I play these, let me explain. So these two rows correspond to two different initial correlations for these covariances. And then in the first column, we're going to look at the evolution of the mean state, where in black dashed, we have the exact mean, and then in blue, we have the mean estimated from the ensemble. In the middle here, we have the covariance matrices. So we have the ensemble covariance matrix estimated from 800 ensemble members. We have the covariance from this full rank MMP transpose for reference, and then we also have the exact covariance matrix here. On the far right here, we're going to look at the evolution of the variances, so effectively the diagonals extracted from these matrices here, where in gray we'll have the exact variance, in orange we'll have the ensemble variance, and then this red dot dashed will be the variance extracted from this MMP transpose evolution. So I'm going to play this top video here. And what I want first to notice is if we focus on the evolution of the mean state here on the left, we see that the ensemble mean is very good at capturing the evolution of the mean state. But if we look at the rest of this figure, particularly the covariances and the variances, we see something quite remarkable. If I pause this here and we look at the variances, we actually see something quite interesting. We see that the variances are significantly inaccurate. And in particular, if you notice, not only do we see regions of variance loss, we see regions of variance gain. And so there's a lot of discussion of variance loss in the literature, but in this example, we see that there's something much deeper going on here. Now, not only do we have a problem in the variances, but we can also see that there are issues in the covariance matrix as well. In particular, in this region where these correlation links become tight, we see that both the ensemble covariance and the covariance from MMP transpose starts to have issues that then gets propagated through the rest of the covariance matrix in time. Now, these errors persist as we move towards correlations that are relatively well resolved, and we can see that in this bottom panel here. So this is a slightly larger correlation length, and we start to see similar errors, which I'll play these now about the same time, in the variance as well. So the mean state is evolving fairly reasonably, while the variance is exhibiting loss and gain, and the covariance is starting to exhibit errors as these length scales become small. Now, we can look at this a little more systematically by comparing the errors as a function of ensemble size. So in this figure here, we're looking at the average percent error in the mean state, the variance, and the correlation as a function of ensemble size here on the x-axis, where I've listed the ensemble sizes at the bottom of the slide here, for three different initial covariances, where this 0.1 and 0.25 values correspond to the videos on the previous slide. And so we can begin by looking at the errors in the mean state, and what we can see right away is exactly what we expect. The errors in the mean state are relatively small, and they decrease exponentially as ensemble size increases. Now we can compare that to the errors in the variance. And the first thing that I want to note here is that first, the y-axis scale has increased, and I've added 3 additional curves, and these curves correspond to the errors in the variances from this MMP transpose, which are constant because they don't depend on ensemble size. And so there are 3 observations one can make here in the variance errors. First is that the errors are in order of magnitude larger than the mean state. The second is that these errors depend on this initial correlation length scale and become larger as the correlation length scales decrease. And the second is that sampling errors don't seem to be a major issue here. And in fact, what we would observe is that these ensemble-based schemes converge to the discrete problem defined by this MMP transpose, but none of them can actually approximate the exact continuum covariance solutions. Now, we can see that this also is occurring in the correlations as well. So here we're looking at the correlations, and I will note that the y-axis scale has changed again. So we've increased in errors by a factor of 10, but the general behavior in the errors and the correlations is about the same. We see this increase in errors as correlation lengths become small, and convergence to this discrete problem and not the continuum solutions. Though I will note that this convergence is a little bit slower, but this is an artifact of the fact that these correlations do have spurious long-range errors, and we're using the Frobenius norm to measure that. But the general phenomenon here, at least, is the same. And so through these examples and through recent work, the insights that I have been able to gain here by studying the continuum covariance propagation equation is that while the propagation of the mean state is reasonably accurate, the corresponding ensemble covariances are significantly inaccurate in comparison to the continuum covariance dynamics, which we now understand and know. And in particular, what we've observed is that these errors in these ensemble covariances increase as these correlation lengths become small. And sampling errors really are not the dominant issue in the problem. And really, the underlying problem that we've seen in the evolution of these covariance matrices actually lies within this discrepancy. In particular, this discrepancy between discrete covariance propagation, which again is constructed from the discretization of the state dynamics, and the nature of solutions to the continuum covariance dynamics, which we now understand. And in particular, what I've been able to do through my body of work is really be able to identify this discrepancy because we now understand the behavior of these continuum solutions. In particular, by studying these PDEs, we've been able to identify the existence of special solutions, in particular these white noise solutions. And it turns out that these standard approaches to discrete covariance propagation do not respect the nature of these continuum solutions. We can see this at a very high level by observing that covariance propagation effectively operates along the columns and the rows of the covariance matrix, which amounts to averaging across the covariance diagonal. Now, one should be a bit skeptical of that because the covariance diagonal, as we know, is already a maximum, but this averaging behavior is particularly problematic due to the existence of these special solutions that we've been able to study by looking at their corresponding PDEs. Now, as I said from the beginning of this presentation, really the goal of this work here is to bring to light this fundamental issue for discrete covariance propagation in the context of these advective systems, which we can do now because we understand the continuum dynamics and can then analyze this discrepancy within discrete space. And what I would like to say is that now that we understand the problem, we can then now try to move forward and come up with solutions. The next speaker, Annika Vogel, will be talking about one approach to solving this using the parametric Kalman filter. But I don't have any really general solution to this problem, though I do have some ideas. And I would really like to open this to the community to start thinking about ways that we can try to tackle this problem, whether this is through targeted numerical schemes or other ideas as well. So with that, I think I'll go ahead and conclude. Here are some references as well as contact information for anybody who would like to look at these preprints or talk with me offline. And with that, I am happy to take questions.
Thank you very much, Shay. That was a really interesting talk. Let's take a look at the Jopad to see if there are any questions yet. Yeah, there is a question from Lars Nerger. He says, actually, stating that the covariants are not correctly propagated, you seem to imply that an ensemble is not able to correctly propagate the PDF. Does that contradict the theory behind, for example, particle filters?
So that's an interesting question. And what I would say to address your question, Lars, is that if you're unable to accurately capture the covariance, then the corresponding PDF is also inaccurate as well. And so I think this would then be an issue that would arise in whatever data assimilation implementation that you are using. So I didn't talk about particle filters at the beginning, but this would extend to particle filters as well, really because this is rooted in the continuum covariance dynamics. itself. So I would say, to answer your question, yes, if you can't accurately propagate the covariance, then you're also not propagating the corresponding PDF as well.
Very well. Lars says thanks. There are no more questions. Well, uh, I was wondering if you could discuss a little bit the ideas that you have to fix this problem. You said that you had some of them.
Yes, so yes. If I jump to the slide here, so this is a still from one of the animations that I showed that'll kind of highlight this idea that goes back to an idea introduced by Steve Cohn in 1993 and is related to the parametric Kalman filter. The idea here is that, as I showed before, we have actually an exact equation for the variance, and one can also derive an exact equation for a correlation length scale. And so what we can do is, instead of maybe trying to implement a variance inflation scheme, which is non-trivial here because you've got regions of variance gain, why don't we actually just approximate this exact variance here? And then in order to recover the covariances, we can then say, okay, we have access to information about these evolving length scales. So we can evolve the length scales and then approximate the corresponding correlations using a parametric correlation function, which the idea is more or less similar to trying to build, say, like a multi-scale localization function, which would be able to keep these large scale features without maintaining these errors in this small region. And so this is referred to as local covariance evolution, again, introduced by Steve, and then relates to the parametric Kalman filter by Olivier Pennacoke, and some ideas that Annika will talk about next. So if anybody's interested in this discussion on this type of approach, I'm happy to talk more about this offline.